Hey, how we doing, kids? This is Stats with Glenn. This is I think we're looking at chapter 4. Yeah, chapter on correlation. And I know I said this about the chapter on Z-scores, but man, do I love the chapter on correlation. Correlation is such a profoundly important and useful statistic. We think about correlations all the time and might not even know it. Correlation is pretty much a relationship between two continuous variables. Is how fast I drive on the highway related to how many tickets I end up getting? Is how hungry I am at the grocery store related to how much money I spend at the grocery store? Is the number of hours that I play Fortnite negatively related to my GPA in high school, as an example? These are things that we think about all the time. Just want to say it is 2020, kids. Spring 2020, kind of a special time in our nation's history. Are we going to get through this? Yes, we are. Happy St. Patrick's Day. This is March 17th, and this is a special St. Patrick's Day edition of Stats with Glenn. Correlation. Correlation corresponds to a relationship between two continuous variables. So an example that we've got in chapter 4 has to do with a situation that I think is probably affecting families around the world: playing video games and academic success. So something to think about. Is video game playing, I'm going to write the word negatively. I'll stop and tell you what this means. Negatively related to academic success. When we have a correlation, we can think about a correlation in a couple of different ways. There are 3 basic patterns of correlation. A is what we might call positive correlation. The positive correlation, high X goes with high Y, and low X goes with low Y. So positive correlation, someone who scores high on X tends to also score high on Y. So now we're looking at relationships between 2 variables. We're still under descriptive statistics, by the way. And someone who scores low on X tends to score low on Y. So this might be like the relationship between studying and GPA, where someone who studies a lot, high in the X variable, tends to get a high GPA, high in the Y variable. People who study a little, low in the X variable, tend to score low on GPA, the Y variable. So that would be a positive correlation. We'll talk in more detail about how we can think about a positive correlation, but just to sort of know the guts of it. B is what we call a negative correlation. Here we have the opposite. Here we have what we call low X going with high Y, and a high X going with low Y. Okay, that's the example we can use has to do with this question here. Is video game playing negatively related to academic success? When I was in college, I remember, I think it was 1989, and someone got Nintendo and started playing Tetris in the dorms. in our floor. And I remember everyone until about 2, 3, 4 in the morning would be playing Tetris in that room. And I remember their GPAs plummeted and they started giving the Nintendo away. And everyone had the Nintendo for at least a couple of days, and everyone stopped going to class and everyone stopped doing work. It was a terrible time with the University of Connecticut kids. We got past it. But I will say, I remember thinking, man alive, video games hijack the human mind and have the capacity to take us away from all the things that we gotta be doing, including schoolwork and so forth. Is video game playing negatively related to academic success? If that is the case, and you'll see the example we're gonna work out, I think it is the case in the example. Low X, meaning someone who does not play a lot of video games, might go with a high Y or a high GPA, and a high X, someone who plays a lot of video games, might go with a low Y or low GPA. Negative correlation. Finally, C, we have essentially, I'm kind of writing the approximately sign here because it doesn't have to be exactly 0, but there's what we essentially call a zero correlation. The short version of a zero correlation or of an approximately zero correlation is X and Y are unrelated to each other. So this is the third thing that can happen. X and Y might be unrelated to each other. So these are our different general patterns of correlation. And we're going to start with an example, and then we'll dissect this example in terms of the different ways that we represent a correlation. Okay, so is video game playing negatively related to academic success? If we were going to do this study, we would want data on 2 variables. We would want data on video game playing. Maybe the number of hours per day someone plays. And we would want data on how someone did on some academic outcomes. So let's just say quiz score. So importantly, when we're doing a correlation, the data from X and Y are yoked to each other. That means that they're connected. So this first score of, I'm going to put 0, so this person played 0 hours of video games. That person got a quiz score of 8. Okay, so it's the same person. This next person played 3 hours of video games, got a quiz score of 5, and the final person played 9 hours of video games, bad idea, and got a quiz score of 2. Okay, so just real simple data here. So how can we represent this relationship? We can do this in 2 ways. We can represent the correlation graphically. And to represent a correlation graphically, we're going to create what we call a scatter plot. There are 5 steps that I have on page 67 in creating a scatter plot. So if you've got the book, you can just take a look at those steps, but it's pretty straightforward. The first thing you do is decide which you're going to call your predictor variable and which you're going to call your criterion variable. So you're going to decide which is your predictor variable and which is your criterion variable. Mathematically, it actually doesn't matter. And there's a lot of times where it's a coin toss. It doesn't really matter. It matters more for the next chapter. The next chapter on statistical prediction, which one is your predictor variable and which one is your criterion variable ends up mattering quite a bit. So I want you to get used to the idea of trying to figure this out. Your x variable is what we call our predictor variable. It's kind of the one that you think is predicting outcomes on the other variable. And that other variable, sometimes we'll call it the outcome variable. It's officially called the criterion variable. So the predictor variable is x, and the criterion variable is y. Like I said, mathematically it doesn't really matter, and sometimes it's totally arbitrary as to which one you pick as x or y. Next, we're going to draw x and y axes. Okay, so scatterplot, unlike our frequency polygon that we did in the other chapter, which represented a single variable, we're now representing two variables concurrently or at the same time. Here's x and here's y. This is number of hours of video game playing, and this is your quiz score. 3, we're going to label these axes. And the video game goes from 0 to 9, so I can go 0, 2, 4, 6, 8, 10. The way that you do that is kind of arbitrary. It's up to you. Use whatever the scale is and figure it out. There's more than one correct solution to that. And the quiz scores go from 2 to 8, so I use the same thing. 2, 4, 6, 8, 10. That's actually step number 4, which is the range of possible xy's. Step 5, we're going to make a dot for each xy point. So we're going to make a dot for each xy point. Okay, the first xy point. X is 0, y is 8. Okay, so here's 0 on x, here's 8. So that dot goes right there. Each dot represents a particular individual, representing both that person's x score and that person's y score. This next person got a 3 on x and a 5 on y. So that person's right here. And the final person got a 9 on x and a 2 on y, which is like right here. Done. That is the scatterplot. Scatterplot gives you information. It gives you 2 basic pieces of information. First thing it does is it gives you information about what we call the correlation direction. Okay, remember I talked about a positive correlation where low x's go with low y's and high x's go with high y's, and a negative correlation where low x's go with high y's and high x's go with low y's. This is a negative correlation. So just an example of the correlation direction, you could get a negative correlation. And again, that's low x, high y, this pattern here, overall, is a negative correlation. The pattern of the correlation direction speaks to a pattern overall. It's not about any individual score, and there will always be scores that deviate from the general pattern, but it's commenting on like the overall pattern. So the overall pattern here is a negative correlation. You might remember from algebra in high school or whenever you took it, that a line with a negative slope goes down. And in fact, in the next chapter, we're going to come up with a formula for figuring out, this is what's called the line of best fit. The line of best fit, and again, we're not going to get into the details of how to calculate it now, we'll get into that in the next module, but the line of best fit is the line that mathematically best approximates each of the actual raw data points. It is the line that is closest on average to each of those data points. If that line that mathematically is closest to all these data points has a negative slope, right? You remember from algebra, this is a negative slope. You remember that's a positive slope. If it has a negative slope, then we call that a negative correlation. So the scatter plot gives us information about the correlation direction. Is it positive or is it negative? If it kind of goes down like that, from left to right, that's a negative slope, that's a negative correlation. If it kind of goes up and to the right, then that's going to be a positive correlation. So the scatter plot visually gives us information about the correlation direction. It also gives us information about the correlation strength. The easiest way that I can think about putting this is that you look at the degree of scatter. A strong correlation is such that the dots in the scatter plot deviate little from the line of best fit. So with a strong correlation, the dots in the scatter plot deviate little from the line of best fit. Here, in our example, I'd say we have a pretty strong correlation, because you could have a negative correlation that is kind of like this. If you look at this correlation, maybe I can stack the deck a little more, you can see that it's generally a negative correlation, but let's say this is like the line of best fit. The dots are not all that close to the line of best fit. Whereas in our actual example here, the dots are very close to the line of best fit. So when the dots are really close to that line of best fit, you have a strong correlation. A weak correlation exists if the actual dots in the scatter plot do not tend to be close to line of best fit. So the dots tend to be all over the place, such as this example that I put right up here. So scatterplot is useful. It gives us information about the correlation direction. It gives us information about the correlation strength. It is visual. If you're a visual learner, you like that. But there's a problem with the scatter plot, which is it kind of has the eyeballing problem. So when you look at that correlation, even though it looks like a very strong negative correlation, you're just kind of looking at it and making that inference. And statisticians don't really always like that. We like our math and we like our equations. So there's another way to think about correlation, which is more mathematical. And that is the statistic called R, lowercase r. R is a mathematical way to capture a correlation. So I'll tell you two things off the bat about R, and then we can get into the details of computation. R ranges from -1 to +1, with 0 in the middle. So R is a lot like your scatter plot. R tells you information about direction, but it tells us information about the direction because if it's positive in sign, that means that the correlation is positive and will have a positive slope. And if it's negative in sign, and you'll see by definition half of the R's will be negative, that means that it is negative in slope. So simply the sign of R automatically tells you about whether your correlation is positive or negative. If it's a positive R, that means your correlation is positive. Low X's go with low Y's, high X's go with high Y's. If your sign of R is negative, that means your correlation is negative. That means low X's go with high Y's and high X's go with low Y's. If your correlation is close to 0, that means you have a weak correlation. So the second thing that R tells you pertains to the correlation strength. So there's info about correlation strength. As R approaches either 1 or -1, I know it's on videotape so you can watch that again, but it's so important that I'm going to repeat that. As R approaches either 1 or -1, R gets stronger. So whether a correlation is positive or negative has nothing to do with whether a correlation is strong or weak. That's a very important point. If you don't get that, you're missing a really important point about correlation. Related, as R goes towards 0, R gets weaker. So correlations that are near 0 are weak. Correlations that move toward either -1 or +1 get stronger. So you can have a strong positive correlation, you can have a strong negative correlation. The other cool thing about R is that it's really fun to calculate. And what I love about calculating R is it is incredibly intuitive. So it's a lot of equations, and it seems like if you just look at it, it seems like a lot, but it's actually, every single step is completely intuitive. So let me start with the formula for R. R equals the sum of Zx, Zy divided by N. Now when I'm teaching this in person, I like to tell my students, if God forbid, I had to take a phone call and had to leave right now, and you had these numbers over here, and you had this formula, and I was like, oh, noodles, I gotta get going, kids. Sorry, you'll have to figure this out on your own. Do you think you could figure it out on your own? I know you're watching at home, kids, and you should raise your hand and say yes, and I'll tell you why. Because you can derive this, okay? R equals sigma zx zy. That just means the sum of all the zx's times, right? If they're just next to each other, that means times all the zy's. You could do that, divided by n, the number of cases, which is 3. You can do that. So computing the correlation, computing R, is something that you have all the capacity to do right now if you had to. But don't worry, I'm gonna walk you through it. Okay, so R equals sigma zx times zy divided by n. You'll see as we work through the numbers how incredibly intuitive and useful this actually is. So we need to subtract out, we need to get zx, right? Because if this is the formula, first we need to get all the zx's, then we need to get all the zy's, and then we can work this out. So first we gotta get zx's, remember z of x, and now we're gonna start putting little subscripts, by the way. So z of x equals x minus m of x divided by standard deviation of x. So you see those little subscripts? Just like what we did before, same z-score formula, except now I'm putting the little subscripts for x because we now have a y variable as well. And we're gonna have different subscripts depending on whether we're talking about our x variable or y variable. It's just nomenclature or just symbols, just to make it more clear. So we're gonna subtract out m of x. The mean for the x variable is 4. Now we have x minus mx. This is the deviation score, how much each individual score deviates from the mean. -4, -1, +5. And now we have x minus mx square, which is 16, 1, and 25. Okay, now we're gonna come up with the sum of the square deviation scores. Sigma x minus mx square, which is 25 plus 16 plus 1, which is 42. We're next gonna get SD square sub x. Okay, this is the variance. I put the sub x, just meaning we're dealing with our x numbers right now. That's all that little subscript means. It is the sum of the square deviation scores divided by n, divided by 3. 42 divided by 3 is 14. We're next going to get SD sub x, which is the standard deviation, the square root of SD square sub x, square root of 14, which is 3.74. Standard deviation is 3.74. We need that because we're going to compute these 3 z-scores. So the first z-score, remember z of x equals the particular x minus the mean of x, 0 minus 4, which is -4, divided by the standard deviation of 3.74. So this first one is -1.07. This z-score, 3 minus 4 is -1, divided by a standard deviation of 3.74 is -0.27. And the z-score for this score of 9 is 1.34. This is all spelled out on page 73 in the textbook if you need to refer to the details carefully. But those are the z-scores for each x. Again, I always want you to be able to look at a z-score and be able to interpret or explain what that means. This z-score of -1.07 means that the raw score it corresponds to is more than one standard deviation below the mean. The fact that it's negative means it's below the mean. That score of 0 is the lowest raw score we have on the video game playing, so that makes sense that there's a big negative z-score. This z-score of 1.34 is a large positive z-score. That means that the raw score it corresponds to is very much above the mean, and let's take a look at the raw score is 9. So 9 is the highest score. It is very much above the mean. So those are the z-scores for the x variable. Here's the formula for r. We need the z-scores of x, but we also need the z-score of y. Can we do that? Yes, we can. It's the same exact process, but now we're going to do that with the y variable. So we're going to subtract out the mean of y, which is 5. And now we're going to get our deviation scores, y minus m of y, which is 3, 0, and negative 3. Next, we're going to square those, so it's the same process, y minus m of y squared, which is 9, 0, and 9. And now we need the standard deviation because we're going to get all the z of y's. To get the z of y equals a particular y minus the mean of y divided by the standard deviation of y. So we need the standard deviation of y so that we can compute each of these three z of y scores. So first we're going to do sigma y minus m of y divided by, squared. So this is the sum of the squared deviation scores for the y variable. That's just 9 plus 9, which is 18. Easy. SD squared sub y is sum of the squared deviation scores divided by n. 18 divided by 3 is 6. Standard deviation for y is the square root of the variance, square root of 6, which is 2.45. So we need the standard deviation of y so that we can compute all these z-scores. And the z-score is y, each y minus the mean of y, divided by the standard deviation. This first one is 3 divided by 2.45, which is 1.22. This next one is 0 divided by 2.45, which is 0. And this next one is negative 3 divided by 2.45, which is negative 1.22. So those are the z of y scores. Okay, that's all spelled out in detail on page 74. The next step in computing the correlation, remember we're moving toward this. So we got all of our z of x's, we got all of our z of y's. The next thing that's in this equation is we're going to multiply those things together. This is called the cross product of the z-scores. Okay, so that's zx, zy. Cross product of the z-scores. Remember I said that every single step in this process is intuitive and should make sense. That's especially true for this particular step, as you're about to see. So the raw score for this first person is 0. That person did very little video game playing. That person's z-score on x is negative, because that raw score is very much below the mean. That person's score in the quiz was higher than anybody's. And the z-score at 8 and the z-score 1.22 is a relatively high positive z-score. So what's going to happen when we multiply those together, negative 1.07 and positive 1.22, we're going to get negative 1.31. Okay, so that is, just to think about it over here, that is negative 1.07 times 1.22. That is a cross product of these two z-scores. So we're going to get the cross products for each z and x. So that first cross product is negative 1.31. What do we know about that? We know that it's negative. There's two ways that that could be negative. That could be negative either by z of x being negative and z of y being positive, or that could be negative by z of x being positive and z of y being negative. You remember, a negative correlation means low x's, which would have a negative z-score, go with high y's, which would have a positive z-score, and vice versa. So when you're computing your cross products, when you get an abundance of cross products that are negative, that is feeding toward a negative correlation. There's the two ways that a negative cross product comes about, either as high X and low Y, or low X and high Y. So that first one is negative. Let's take a look at the second one. This Z of X is negative 0.27. That Z of X is 0. This one kind of cancels out. That cross product is 0. Finally, this raw score is 9. That's very much above the mean for the X variable. This Z of X is 1.34. So that's a large positive Z-score. And this Z of Y, negative 1.22, is a large negative Z-score. High X goes with low Y. That cross product of negative 1.63. Okay, take a look at the formula. We also need the sum of the cross products. So the sum of the cross products simply means we add up this column. That's sigma Zx, Zy. Nothing fancy. Again, if you just saw these symbols and you didn't know what they meant, you'd be like, what's going on? But everything here should make sense. The sum, sigma, of the cross product of Z-scores, we're going to add those up, and that equals negative 2.94. Cross product of the Z-scores is kind of cool, but there's something it does not take into account, which is the N. So based on just the sum of the cross product of Z-scores, you don't know if that's based on 3 different scores or 100 different scores or 1,000 different scores. So what we're going to do, which is the kind of thing we've been doing throughout the semester whenever we have a situation like this, is we're going to take the average of that. And that's what R is. R is the average. We're dividing by N. It's the average of the sum of the cross product of Z-scores. It's just taking that sum of the cross product of Z-scores and looking at it relative to the number of cases that we have. So R equals sigma Zx, Zy divided by N, which is negative 2.94 divided by 3, and that is a whopping negative 0.98. That equals R. Now remember, R tells you 2 things. It tells you about the correlation direction and tells you about the correlation strength. Further, your R should go hand in hand with your scatter plot because they're just different ways of giving you the same information. So here's our scatter plot. Remember we said it's a negative correlation, and you remember we said it's a strong correlation because the dots are relatively close to the line of best fit. This R of negative 0.98 is saying the same thing. It's negative because it has a negative sign. That means low X's go with low Y, or high Y's, and high X's go with low Y's. And it's strong because negative 0.98 is very close to negative 1. So you remember R goes from positive 1 to negative 1, and as R gets closer to either positive 1 or negative 1, it gets stronger, and a correlation of negative 0.98 is very close to negative 1.0. So that's a really strong negative correlation. So that's the information we have. That's how you can take these raw numbers and convert them into an R. You can do that by converting them to R. You can do that with a scatter plot as well. They both should give you real similar information. The benefit to R is it's computational. And you'll see as we get into the next chapter, which is about statistical prediction, R is really powerful and useful. One final bit of information about R that every stat student in the world must learn has to do with interpreting R. So while you can tell that I'm a big fan of R, and I think it's cool, and I could calculate R's all day long, there's a problem with R, which is R is a correlation, or represents a correlation. And it's a little complicated as to why this is. Nice. We're good, we're good.
You're good.
It's a little complicated as to why this is, but that was funny actually. I think we should keep it.
Okay.
So R is correlation, and when you have a correlation, you don't necessarily have information about causality. You won't really fully understand why until you take a good course on research methods in the behavioral sciences. But the real short version is this line. Correlation does not necessarily imply causation. Which means that just because you know that two variables are correlated with each other, you don't necessarily know why they're correlated with each other, unless you have done what is called true experimental research. The whole process of true experimental research, again, is kind of the content of your research methods class or your experimental psychology class, another very important class, by the way. But unless you've done true experimental research, when we see a correlation, we cannot infer causality. So if Rxy, meaning if we have a correlation between R, or if we have a correlation between X and Y, there's a few possibilities. A, it could be that X causes Y, which we'll represent with a direct arrow like that. It could be that X causes Y. I'll give you an example. There's a famous example in the literature about the relationship. So this is an EG, for example. The relationship between watching violence on television and aggressive behavior. So lots of research has shown that there tends to be a small but positive and reliable correlation between how much violence a kid watches on TV and how much aggressive behavior that kid engages in. And there's been a lot of questions in the literature as to whether this is a causal relationship, and if so, what direction that goes in. So here's the possibilities. Let's say that X, in this case, remember I talked about the predictor variable and the criterion variable. So the predictor variable predictor of the X variable is watching violence. And the criterion variable, the outcome variable, or the Y variable, is aggressive behavior. If you find a correlation between how much kids watch violent television and how much aggressive behavior they engage in, there's a few possibilities as to why that might be the case. It could be that watching violent television makes kids aggressive, which a lot of people who do research in this area are trying, I think, to sort of make the case for. So it could be that X causes Y. But since we haven't done true, or if we haven't done true experimental research on this topic, then we don't know if it's X causes Y, or maybe it could be that Y causes X. Just knowing just a correlation between X and Y, it could go either way. So it might be that kids that engage in aggressive behavior just really are reinforced for that and really enjoy that. And when they get home and watch TV, they're like, oh, look, that person's doing what I do at school. What a great TV show. Let me watch that, as an example. So it could be, when we see the correlation between X and Y, it could be because watching violence causes aggressive behavior. But if we haven't experimentally controlled for anything, it might just as well, just as possibly, be the case that engaging in violent behavior, aggressive behavior, causes watching violent television. Alternatively, I'm going to give you another or. There could be what we call a third variable might account for both. So if we simply know that there's a correlation between X and Y, and we haven't experimentally controlled for anything, it could be that X causes Y, we don't know. It could be that Y causes X, we don't know. Or it could be the third variable. This is like the famous third variable problem. It could be that Z causes both X and Y, and that X and Y are related to each other, but that they're only related to each other, and that's why I have this dotted line, not because they're causing each other, but that they're both caused by a third variable. As an example, I'll put socioeconomic status. Maybe kids who are really poor have parents that are paying less attention, or maybe parents that are not home, or maybe fewer adult supervisors at the home in general, because parents are out working, because they're poor, so they need more money, right? So this kind of goes hand in hand. And maybe in that kind of household, the kids are watching whatever they want, and they find it fun to watch violent TV. And maybe since they're not supervised, they're beating each other up at home because that's how they have a good time. Maybe simply being poor and not having parental supervision and to lead to watching those kind of TV shows tends to lead to aggressive behavior as well. So this could be the third variable problem. So when you have a correlation, and again, I love correlation, so while correlation is really cool and it can tell us very much about the relationship between two variables, it is also limited, and it's limited in terms of the issue of causality. So just because you know there's a correlation between two variables, you do not necessarily know whether one of those variables causes the other or vice versa. That's this chapter on correlation. This has been Stats with Glenn.